So let us take an example where we are trying to do housing price prediction. I'm taking a very simple regression example to explain the algorithm that is working behind the scenes. What exactly is forward propagation? What is back propagation? What is gradient descent? How is the network trained? And here it is a simple neuron. We are not even taking a neural network. We are taking an example of a simple neuron to explain the process of training. And then we will extend this to a bigger use case going forward. So let's say, once again, based on the input x's, square foot, neighborhood, and bedrooms, you are trying to predict the price. It is a typical price prediction use case that we are trying to solve. So based on the input x's, we are trying to predict the price. So we have square foot, neighborhood, bedrooms. So based on the square foot, neighborhood, and bedrooms, we are trying to predict the price. So we have a simple artificial neuron that we will use for the computation. We will give this as inputs. X1, X2, X3 are the three inputs that we will provide. We will multiply these input x's with the weights W1, W2, W3. We'll add a bias and we will calculate a predicted value. Okay, this is the way how we'll work it out. So again, X1, X2, X3 are the three inputs. We will feed that to the neuron. We will multiply those inputs with the weights. We'll add a bias and we will calculate the predicted value of Y. Now, if you remember in linear regression, if you just go back to that conversation for a minute, if you remember, we were trying to find the line of best fit, right? That Y equal to mx plus c, if you recall for a minute, that is the best fit line we were trying to build, right? In that entire conversation of the linear regression, we were trying to create a best fit line, right? We were trying to create what is the line of best fit. And there are different lines that are possible. If you recall that scale that we talked about, there were different lines that you could draw. So if you take a different slope and if you take a different intercept, if I give you a different value of m, and if I give you a different value of c, right? So there's actually a very nice video that or animation that talks about it. I can take you to that animation. A very nice animation that actually talks about that linear regression process, whatever I'm trying to explain here. So look at this one, right? So you can see. So imagine this is the set of data points I have right now, and so there are infinite number of different M and C's you can take, right? If let's say this is the set of data points I have, if I want to do linear regression, I can take different C's and I can take different M's, right? I can rotate the line in different ways, right? You can see how I can take a different slope and how I can take a different intercept. So by taking different slope and intercept values, I can build different lines. And out of all these possible slope and intercept values, this is like that Y equal to mx plus c. So we can try different M's, we can try different C's. And by doing that, we are trying to find what is the ideal M and C. That is the crux of linear regression that we talked about, right? Now, if you extend this to the neuron, and because the neuron is also a linear model, instead of M and C, you are trying to tune W and B, but the idea is exactly the same. Just like here, we are trying to adjust and we are trying to take different M and C values. Similarly, here you are trying to take different weights and bias values. So the end result of a neuron training is we are trying to narrow down to the best possible value of weights and the best possible value of bias. We are trying to find out what is the ideal weight and what is the ideal bias. That is what we are trying to do. What are the weights and biases of the neuron? But obviously, when we start the training process, we will not know that. We will not know what is the weights and what is the bias right at the outset. Right at the start of my training, we will not know. We will not know what is the weight and what is the bias, right? So what do? We start with random weights and biases. So right at the start of the neuron training, we start with a random value of W and a random value of B. And then we do something called forward propagation. What is forward propagation? Forward propagation means you're going forward. You are taking those weights and bias values that you initiated. This is step one. Step two is this. you use those weights and bias values to calculate the y predicted. What is y predicted? W1 x1 plus W2 x2 plus W3 x3 plus bias b. This is the predicted value of y that you're getting from those initial random values. So you add the predicted column here. I'm just trying to demonstrate here for you. So now what you do is you calculate the loss. So you're saying, hey, I took some random weights and biases, and using those random W's and B's, I'm seeing how my network is doing. That means if I had used those weights and biases for the computation, my predicted values would have come like this. Are they similar to the actuals? Please calculate a loss. Please calculate a loss. Are they similar to the actuals? So you will calculate a loss. You will calculate MSE loss, MAE loss, the different loss functions that you have. And you will see some loss, right? The predicted will never match the actuals. You will see some loss. There'll be some delta, the error. And then you will do something called gradient descent or backpropagation. Now, what is gradient descent? Explaining this in very simple terms, gradient descent is the process of updating the weights and biases. Simple, straightforward. You got some loss, right? You saw that, okay, the predicted is not matching the actuals. Step one, you took random W's and B's. Step two, you calculated predicted value. And step three, you see the loss is pretty high because naturally with the random values, it will never match, right? The loss is very high. With those weights and biases, I am not getting the right predictions. My predictions are far from the actuals, far from the actuals. So I will do gradient descent and I will update the weights and biases. This is called backpropagation because you're going back and you're backpropagating and you're updating those initial weights and biases that you took. So you update the W's and B's. Then with that updated W and B, you again do forward propagation. You again calculate the predicted value with those updated W's and B's now. And naturally, this time it will be little better. It will be little better, right? Because you did something. You went back, you updated the weights and biases, you did something. And based on that, when you recalculate your loss, the loss would have reduced a little. It's like we all make incremental improvements in our life, right? We all start with something, we'll make lots of mistakes, and then somebody gives you feedback. So think of this gradient descent as a feedback. So when you get that feedback and when you fine tune those weights and biases a little, the next iteration, your loss would have reduced. You would have been slightly better. But then there is still some loss, right? Again, what do you do? Again, you go back propagate, update the weights and biases. Again, using those updated weights and biases, you calculate the predicted value. Again, calculate loss. The loss would have further reduced, right? But it still is there. So you keep doing this over and over and over again. And each of these cycles is called an epoch. So what is an epoch? An epoch is like a cycle, right? It's an iteration, right? It's an iteration. So one forward propagation and one back propagation cycle together is called an epoch. So you continue doing this for many, 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 many epochs until your loss becomes stagnant. Your loss minimizes to the point where it no longer reduces further. And then there are other kind of things like training loss, testing loss, which I'll come back to later. But this is the core idea how we train a single neuron. The idea extends the same for a neural network also. This is a single neuron. So you start with random weights and biases. You find out the predicted value. You compare with the actuals. You calculate the loss. And then you do gradient descent, where you go back to the previous steps and you update the weights and biases. And you keep doing this over and over and over again. And with every gradient descent, with every weights and bias update that you do, you make the network slightly better. So now when you update the weights and biases, your predicted values will be slightly closer to the actuals. It will be slightly better. The loss will slightly reduce. So that's the assumption we are making. By making small incremental changes, by making small updates to the weights and biases, by giving that small feedback, think of gradient descent like a feedback. So by giving that small feedback, we are able to make the network better. And that's what we try to do in deep learning at a very high level. So next time you hear about an algorithm called backpropagation, somebody talks about, there's something called backpropagation algorithm. This is exactly what they're referring to. So this is the backpropagation algorithm that is working out behind the scene. Now this is a slightly more technical. This is, I would say, this is the level to the technical, depiction as to what is going on behind the scenes. So I'm not going to get too much into this topic, but at a very high level, if people can relate to it, I'll just briefly walk you through it. So this is the thing. You can see this is the neuron. This is the input axis, weights W1, W2, B, and this is the computation that we are doing. Okay, and you try to find out your weights and biases such that MSE is minimized. MSE, we are dealing in the context of a regression problem. You will try to minimize your mean square error, and this is the loss function for mean square error. And if you take a look at it, this is actually how the weights and bias updations are happening. Again, start with random W and B, forward propagate, compare with actuals, calculate loss, and update the weights and bias. This is the formula for backpropagation. Okay, so the new weight equal to old weight minus eta times some change, and the new bias equal to old bias minus eta times some change. Okay, now this formula you can completely ignore. It's not that relevant right now. But what is important, the key learning from this particular slide is this part called eta. Very, very important. We will discuss this in a lot of detail as we go along, as we train neural networks. Eta is a very important thing. Eta stands for learning rate. Okay, so what does its eta stand for? Eta stands for learning rate. So as we come to the hands-on exercises, we will see how we can use eta going forward. And using eta, you can tune how the network is learning. You can tune the network training in a lot of detail. So just to give you some context, if I say eta equal to 0, we'll take an extreme case. If I take the learning rate to be equal to 0, zero learning rate means what? That means no learning is happening. If I take the learning rate to be equal to 0, zero learning rate means there is no learning that is happening. That means the new weight is equal to the old weight. So here, if you take eta equal to 0, that means the new weight is equal to the old weight. There is no change in the weights. And if you take learning rate equal to 0, the new bias is equal to the old bias. So the weights and biases will not get updated. That means there is no learning happening. So learning rate 0 is very bad, obviously. The whole idea, the whole success of gradient descent, the algorithm lies in updating the weights. You want to update the weights, right? You want to give feedback. You want to make those small improvements. If you're not updating the weights only, then how will the learning happen? Nothing will happen, right? The learning rate 0 is bad. On the contrary, another important thing is a very high learning rate is also bad. So as we start doing the demos, you will realize that whenever you set a very high learning rate, the network doesn't train that well. Because if you set a very high value of eta, the changes will become too unstable. There will be too many, too many random, too big changes that will happen. Okay, so it's like saying that if your eta is a very high number, then W new equal to W old minus this, right? If this number is very high, the updates will be too big. And this is again a general concept in deep learning at a very high level, that we should try to make small updates, not very big updates. So as you update your neural network, as you update the weights and biases in your neural network, try to keep the update small. Don't make it 0. 0 means there is no update you're doing. At the same time, learning rate should not be too high, because if you make it too high, the updates become too big. You dump too much. Like, it's like sometimes you learn something, sometimes you learn something else. So you learn too fast. Even fast learning is bad. Too fast learning is bad. So try to make it moderate. So typical, very good default for learning rate as we come to the demos will be something like a 0.01, something like a 0.1. You should definitely take a learning rate always less than 0.1, always, generally. It's a good default. Okay, and certainly, I mean, most use cases, you will see the learning rate is always less than 0.1. So 0.01, 0.001, these are some very common learning rates you will find. So we always try to make small incremental changes. Okay, so this is the important concept. And then obviously, like, this is the concept of how the backpropagation algorithm works out. Whole bunch of theory, but I hope everybody has the general concept now. And this is another very nice presentation which I used to explain the idea of learning rate. So you can see right now, if we take a very high learning rate, this is exactly what I explained a while back. If we take a very high learning rate, what will happen? The loss will not come down. the loss will not come down if my learning rate is very high. So if my learning rate is very high, the loss will not come down. You can see right now, the loss remains high because you are making too many changes. You're taking too big steps. Like, getting it? Like, it's like saying, if you're learning some topic for the first time, I'm giving very broad feedback. Okay, hey, do this. Okay, let's say you're learning deep learning for the first time, and I give an exercise to you. So I'm simply giving an exercise, and without explaining any of these topics now, I say, guys, this is an exercise, please solve it. Will you be able to solve it? Of course no, because most of you are beginners to deep learning, right? Think of it that way. So learning rate high means you're giving, like, you're making a rapid step, rapid jump. I'm just telling you, okay, do this. I'm not giving you the detailed guidance or the detailed teaching. That's a very high learning rate. So you will not learn anything. Loss will remain high. But on the contrary, even low learning rate is very bad. Low learning rate means we will end up teaching the topics fine, but it will be like 5 years before we complete deep learning, right? That's what some of the universities do. The same stuff they are teaching for 5 years. You will do one module, and then next 2 months you will do useless exercises. Some quiz, some absolute useless MCQs and all they will do, right? That is how they stretch the course for 5 years. On a lighter note, obviously. Anyways, so if you have a very low learning rate, if you take a very low learning rate, what happens is you are learning very slow, very slow. So that means the loss will reduce, but the loss will reduce very, 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 very slowly. The objective of a good learning rate would be something like this, something like the green. And there are ways to plot it out. I'll show you how to plot these things, right? So there's very nice. There's some tensor board callbacks and all we can use to, visualize the learning rates and how taking different learning rates you can. So you can think of learning rate like a hyperparameter. We talked about hyperparameters in machine learning. They're like tuning knobs. Remember how different machine learning algorithms, we use tuning knobs like maximum depth and estimators. Okay, we can tune the hyperparameters. They're like tuning knobs. So same way you can think of in deep learning, learning rate is a hyperparameter. You will typically try out different learning rates and find out the one that works best for you. And the optimal one is this. So you want to take a learning rate. A good learning rate is one where you drop very fast. So you learn very fast initially, and then from there it's a gradual training. So I don't want to take forever to teach you like the basics. So the basics we learn very fast. I mean, that's the hallmark of a good training, right? You learn the basics very fast, and then we take enough time to fine tune the concepts and do lots of exercises. And this is the thing. So there won't be too much of a reduction of loss here. It becomes a little stagnant, but that's the thing. That's the concept of a good learning rate.